So I'd like everyone to meet Adrian, one of the newest members of the cryptography community, and the reason I don't get any sleep anymore. Thank you. And here's mommy and daddy. So in a typical scene in the Zhandry household, Adrian would like to tell mommy how much better she is than daddy. Now, in reality, it's quite obvious when he wants to send this message. However, let's suppose that Adrian actually wants to tell mommy that she's better than daddy, but doesn't want daddy to find out. So what are they going to do? So mom will, well, they're going to use public key encryption. So mom will choose a secret key and a public key, give the public key to Adrian, and Adrian will encrypt the message with the public key and send it to mom. And even though I'm listening in on their communication, I can't find anything out about the message. Now here's the problem. Adrian is a baby, and this means his random numerator cortex is underdeveloped, and when he tries to generate random coins, it just outputs 0. So this means that, randomized encryption is not an option for Adrian, because most randomized encryption schemes will be insecure if you use the random coin 00000. So what is the solution? The solution is to use deterministic public key encryption. This is encryption that just takes in the public key in the message, no random coins, always outputs the same ciphertext on the same message. And the advantage is you don't need randomness. So if you have a bad random number generator, or if your random number generator has been subverted or something like that, you're OK. The scheme will still be secure. And there's a couple other features of deterministic public key encryption that might be useful for some applications, like it allows for a public test of equality, which is useful for things like deduplication. But these advantages of deterministic encryption come with some cons. It's harder to construct. Semantic security is impossible. And the reason is pretty simple. If I had a guess of what Adrian's message was going to be to mommy, I could confirm that guess by encrypting the message myself and testing whether it was the actual message. And what this means is that we need unpredictable messages. So rather than in normal semantic security, the message can be just one of two things. For deterministic encryption, though, we need the message to be highly unpredictable. And as a result of this, also, it is no longer the case that security for one message implies security for an arbitrary number of messages. So in our security definition, we need to explicitly handle multiple messages. OK, so in this work, basically what we do is we construct a deterministic public key encryption where the source of the message is an arbitrary computationally unpredictable source. I'll define what this is in a moment. We handle a constant number of such sources that are correlated in arbitrary ways. And additionally, we get chosen ciphertext security. And we get all three of these simultaneously. And our assumption is going to be DDH, except a variant where we actually assume that it's exponentially hard to solve DDH. OK, so here's computationally unpredictable source. I guess the slide's not lining up well, but basically, a computationally unpredictable source for T messages is just a distribution, an efficiently samplable distribution that outputs T messages, as well as some auxiliary information about the messages. The adversary then receives just this auxiliary information, and their goal is to output one of the T messages. And we say that the source is computationally unpredictable if, for all efficient adversaries, the probability the adversary succeeds in this task is negligible. And we're also going to have to make an additional requirement for computationally unpredictable sources that basically all the messages are distinct, and this will become clear in a moment why we need to make this requirement. So for deterministic public key encryption under computationally unpredictable sources, here's the security definition. So we imagine two experiments. In the first experiment, experiment 0, we have the source. We sample from the source T messages and auxiliary information. We also sample a random public key and secret key for the encryption scheme. Now, what does the adversary see? The adversary sees the T ciphertext that obtained by encrypting the T messages under the encryption scheme using the public key, as well as the auxiliary information and the public key itself. And additionally, we'll give the adversary the decryption oracle, and as usual, we'll require that the decryption oracle allows you to decrypt every ciphertext except, of course, the T ciphertext that the adversary received, the T-channel ciphertext. So what deterministic public key encryption requires is that this view of the adversary is indistinguishable from, well, I mean, there's multiple ways to formalize this. This is one potential security definition, the one we aim for in this work. That this view of the adversary is indistinguishable from the case where we replace all of the ciphertext with random strings. All right. And so in this view here, the messages never actually make it to the adversary, just random strings, but the adversary still gets the auxiliary information in the public key. And here it's hopefully clear why we need in the source, we need x1 and xt to be distinct, because in this view, if x1 was equal to x2, then c1 is going to be equal to c2, but clearly here that's not the case because their random strings will most likely be different. Okay, so here's a slide summarizing some prior work. Really, there's a lot more work here. This is just a small sample. But basically, we have a little chart here where on the x-axis is some notion of the complexity for the source itself. And on the y-axis, we have the number of sources that are handled by the constructions. So down here at the bottom, we have schemes that handle a single source. These are, on the left here, are sources that might just have some min entropy. Here's a source that is computationally unpredictable, though with some restrictions. Higher up, we have sources on more inputs, but they require more restrictions on what the actual distributions are. And then up in the upper right-hand corner, we have a construction that sort of does everything you would want. Totally arbitrary sources, totally arbitrary number of sources. The main limitation is that this work, the security is only proved in the random oracle model, whereas the rest of these are all standard model constructions. And actually, there's a reason for this. It's due to Wix in 2012. It's known that no scheme can actually have a black box reduction to a falsifiable assumption, provided that the source is expressive enough and t is super logarithmic. Okay, so where does this work fit on this picture? This work goes right here. So we get totally arbitrary sources for any constant number of sources, with the caveat that we require exponential hardness, and our proofs are going to be not black box. Okay, so this result will sort of build up to it in three steps. So in the first step, I'm going to consider the case of just a single source, and I'm not going to worry about chosen ciphertext queries. To accomplish this, we're going to use a tool called extremely lossy functions that I introduced a couple years ago. So what is an extremely lossy function? For those familiar with lossy trapdoor functions, this is a very similar notion. So it's a function that has an injective mode and a lossy mode. In the injective mode, the function is, well, just that, it's injective. So it's a one-to-one function. There's no collisions. In the lossy mode, the function has many collisions, and the image size is actually required to be very small. For lossy trapdoor functions, the image size is required to be exponential, but just much smaller than the domain. For extremely lossy functions, we actually require that the image of the function is polynomial in size. And for security, we require roughly that the injective mode and the lossy mode are computationally indistinguishable. Now, this is clearly, hopefully, impossible without a little more work, because if the image size is actually a polynomial, and by running in a slightly larger polynomial time, you can start finding collisions in the lossy mode, and obviously there's no collisions in the injective mode. And so in order to maintain indistinguishability, actually we require that there's not just a single lossy mode, but that there's a whole continuum of lossy modes, and the image size of the lossy mode is actually going to be chosen to be dependent on the adversary. So this is basically where the non-black box part of the technique comes from, is that the lossy mode depends on the adversary. But for the purposes of this talk, let's forget that, and let's just say that there's two modes, and in the lossy mode, the image size is polynomial. All right, and what I showed previously was that under the exponential hardness of DDH, we can construct these objects. Okay, another concept that I considered in the prior work was PRGs for computationally unpredictable sources. So, and in the prior work, we only consider the case t equals 1. So here we have a computationally unpredictable source on one input. And basically what a PRG for this is, it's really the same thing as deterministic encryption, except that there's no trapdoor that allows me to decrypt. So instead of having a public key and a secret key, there's just a single key that's public. The message gets passed through the PRG is keyed with the public key, and the adversary receives the public key, the output of the PRG, and the auxiliary information. And require that basically y is indistinguishable from a random string in this setting. Okay, and what did I show previously? That you can actually construct this object from else for any computationally unpredictable source. So what we want to do here is we want to somehow take a PRG, which, as I said, is basically deterministic encryption without a trapdoor, without a way to decrypt, and turn it into an actual public key encryption scheme that allows me to decrypt. And inspired by many prior approaches to constructing deterministic encryption from lossy trapdoor functions, a natural way to do this would be the following. So I'm going to use any public key encryption scheme. My message is going to be fed through an ELF in the injective mode. And that's going to become the input for the public key encryption scheme. And then X is also going to be sent through the PRG, and the PRG is going to generate the randomness for the encryption scheme. And then the ciphertext is just the result of encryption. Unfortunately, this doesn't work, at least not out of the box. And the reason is that how do you decrypt? So to decrypt, well, naturally with the secret key, I can decrypt the ciphertext here to get the input to the encryption algorithm. But then to actually recover X, I need to invert the ELF. And the problem is the prior work on ELFs actually doesn't have a trapdoor that allows for inverting the ELF. The ELF is injective, so it's information theoretically invertible, but there was no efficient way. Okay, so the first contribution to this work is to actually show how to construct ELFs with a trapdoor that allows for inversion. And the idea in retrospect is pretty simple. So in the crypto paper, this was roughly how we constructed ELFs. We iterated a bunch of lossy trapdoor functions at different security levels. But because lossy trapdoor functions are expanding, we needed to basically compress the value at every step in order to make sure that things didn't blow up and get out of control. But unfortunately, this compression kills any ability to efficiently invert. So in this paper, basically what we do is we do a much more careful approach to constructing ELFs, and do so in a way where we don't need to do this compression in between, but instead just very carefully instantiate the parameters of these lossy trapdoor functions so that we can string them together without compression. And then we just use the fact that these lossy trapdoor functions have trapdoors. Each one has its own trapdoor, and then by composing them, we get a trapdoor for the whole function. Okay, and with that, we get a deterministic public key encryption scheme. I don't have time to give the proof, but it's relatively simple and follows from known techniques. Okay, and there's the theorem. Okay, so next is maybe the more interesting part. Okay, now we have a source on one message. Now we want to upgrade this to sources on T-correlated messages. It turns out that basically we can follow the same approach as before, the same scheme. It's just that we need something stronger for our PRG. We need our PRG to be a PRG for computationally unpredictable sources on T inputs. And again, this is basically the same notion as deterministic public key encryption, except that there's no trapdoor. So there's just the public key that's the key for the PRG, and no secret key that allows for inversion. Okay, and you can take the previous theorem and sort of easily boost it to get deterministic public key encryption for a constant number of sources, assuming that you have a PRG for a constant number of sources. All right. So now, so now we've reduced the problem to constructing these PRGs. So how do we do this? So the first idea is, well, we have PRGs for a single source. Maybe we can use them to build PRGs for multiple sources. And one approach that maybe will work is that, well, what if we could ensure that each of x1 to xt were actually use a different PRG? So each x1 was fed through a PRG using key k1, x2 fed through a PRG using key k2, and so forth, where k1, k2 up to kt are just random independent keys. So if we could do this, it's an exercise, but it's pretty straightforward to show that actually y1 to yt are indistinguishable from random, just assuming the security of G for single sources. But the problem is we want a construction where there's just one key, not T independent keys for each input. So how do we actually get this to work with just a single key? So the next idea is, well, why don't we have the actual global key for the overall PRG define a function, and we choose the input dependent key k as some function of the actual input. So the input is fed through this function, determines the key k for the PRG, and then we apply the PRG to that input in order to receive y. But if you stare at this for a moment, it might seem like there's a problem, because we basically need these wires here, the wires that are determining the keys for each input. We need them to have random independent values, or at least values that look random and independent. But they're random and independent values that are coming from a correlated source. So it almost seems as though we have a circularity in that we need the function f to actually be a PRG for correlated sources. So the question is this actually a problem, or can we, so we're trying to construct a PRG for correlated sources, and it looks like we might need a PRG for correlated sources, so what do we do? Yeah, and I don't have time to prove anything, but it turns out we can actually break the circularity by a careful application of ELFs and T-wise independent functions. So basically, the function used to derive the key for an input is obtained by applying an ELF and then a random T-wise independent function. And turns out with some care, you can actually prove that if G is a PRG for a single source, and this is a secure ELF, that this actually does work. All right, so that's correlated inputs. And now to boost to CCA security, I don't have time, so please see the paper. But a number of annoying difficulties arise when trying to get CCA security. So the good news is that we're using trapdoor functions, or some variant of trapdoor functions, and there's a lot of literature in achieving CCA security for both public key encryption and deterministic public key encryption using trapdoor functions. Unfortunately, things don't quite work right out of the box. And the reason intuitively is that, so to get CCA security, we're going to need a variant of ELFs that are called branched ELFs, which basically means there's an additional input that determines a branch of the function, and one branch will be lossy, the rest won't be. But the problem is that the prior work basically gave generic approaches for taking lossy trapdoor functions and converting them to these branched versions. But unfortunately, ELFs are much more delicate than Lossy Trapdoor functions, and it turns out that these generic approaches don't work for elfs. And basically what happens is, if you apply the generic approach to an elf, you're just going to get a regular Lossy Trapdoor function, not an elf, not something lossy enough for the applications we need. So instead, we actually have to open up the elf a little bit more and actually give sort of a direct construction of these branched trapdoor elves, which we show how to do in the paper. And that's basically it. So that's the paper. And with that, it's nap time. Thank you.
Okay, thanks, Mark. Any questions?
So I wonder if you really need this restriction of all the messages within a source to be different, because already you seem to handle the case where, I don't know, when the different sources, some messages might be correlated. So, I mean, it looks like you should also be able to handle. I don't know, maybe modifying the ideal party if needed, because I mean we could account for the.
I mean, it's just a definitional problem. If you allow the messages to be the same, then you clearly can't get the definition described, because the adversary will always be able to identify when two messages are the same. And it's not hard to sort of overcome this and provide a definition that works even when the source allows the messages to be the same. I didn't really consider it in this work, but much of the deterministic encryption literature actually does provide the sort of more general definition that allows for sources where the messages are the same.
So the assumption on the distribution, there's no. It's only that it's unpredictable. But so you are mentioning some applications. Can we make some additional assumptions on the distributions? Maybe would that be useful or?
Yeah, I mean, depending on the application, you might. So a lot of the work on correlated sources, makes the assumption that each individual message has min entropy conditioned on the prior messages. That might be reasonable in some scenarios. In this work, we didn't want to make any assumptions on the distribution. We wanted to sort of consider arbitrary correlations, even where one message completely determines all the others.
Okay, Adi.
The question is not related directly to your construction, but to the kind of security guarantees that such schemes provide. So you gave up on semantic security because you say that it's impossible for the deterministic encryption, but you replaced it by something which, in my opinion, is too weak to be any kind of comfort. And this is that you should not be able to calculate the full XI given the encryptions. I can give you many examples in which you can calculate every second bit in the input, and then if the input was English, it's trivial to find what it was.
Sure. So for the sources, we don't. So for the sources, we don't make any such restrictions. So the sources that we consider, the sources require that yes, the adversary is unable to reconstruct the entire string, but by requiring the adversary to reconstruct the entire string, we're actually considering more general sources. But the security definition for deterministic encryption that we achieve actually is an indistinguishability notion. Let's see.
It doesn't prevent the adversary from finding every second bit in the input. He will know nothing about the other bits. It will satisfy your condition, but it will make it impossible to use if it was English messages, for example.
Fair enough. Yeah, I think you're going to have to take that up with the authors of all the prior works. So this is something I did not consider in this work, but the definite. I'm not 100% sure if other prior works considered stronger notions like what you're suggesting, but certainly much of the work is sort of more like what I describe here.
The right definition should be somewhere in between, not the ability to compute everything, and not being able to know anything about the input, semantic security, but we should find the right middle ground, which might not be easy.
So why does it work only for a constant number of sources?
Good, good. So there's a couple reasons, actually. So one is here, where I said if each of the keys are independent. It turns out that the proof here doesn't work if you have a super constant number of sources. It's sort of like you're basically going to do this hybrid, and things sort of blow up as you blow up more than exponentially as you sort of do this hybrid. And if you have a super constant number of sources, things will fail. And then also just, in terms of getting the proof to work for this construction here, basically the way this works is we switch this elf to be lossy. And then what we say is that even if you knew the outputs, the t outputs of the elf on the different inputs, even conditioned on that information, the source is still unpredictable. But that's only true because we have a constant number of sources. Each source gives me a polynomial-sized set of outputs, and so the t sources together, it's still polynomial. But once I have t greater than a constant, now I have something super polynomial. So it comes up in a couple places.
Okay, thanks again. We can take further questions offline, of course. So let's thank Mark again.
Thank you.